Alrighty, so we're back to section 2.2, and we're going to be talking about a little tie-in today with motion, and then what we call these higher order derivatives. We'll actually talk about this first and then motion second. So a bit about notation here. So we have a bunch of these mathematicians that are credited with the notation that we use in calculus. So, there's like, I don't know, disagreements or however you want to organize it, that these guys, Lagrange, Euler, and Newton, right, are responsible for like function notation. So that's the derivative, that we've been using all along, okay? So when we say that out loud, we say that this is f prime of x. So I just want to make sure we know how to pronounce these things. Well, a higher order derivative means something further down the line, which would be f double prime. Oh, hey now, back it up. F double prime means the second derivative, right? That means to just take the derivative of the first one. So you're just taking the derivative again. But we always say f double prime. What all the naughty students say is f prime prime, and that ain't right. So try to practice saying f double prime out loud to yourself now. Now this German guy, I think his name is Gottfried Leibniz, he came along and worked with a different notation on his side of Europe, I guess, that we are working on. So the way that he wrote the first derivative is with that dy dx notation. Okay, so the way that we say this, you can just say literally dy dx. We don't really pronounce the divider. Or if you want to sound super fancy, you can say this is the derivative of y with respect to x. And we'll talk about what that means in a minute. Now, he doesn't have a great way to indicate the second derivative. The way he comes up with it is to do d squared y over dx squared. And I don't even really think that those are squareds. Those are just indications that we're talking about the second iteration, right, of a derivative. So the way that we would say this is just the second derivative of y with respect to x. There's a power of 2 in both places, but it just means to take the second derivative. So you're not changing x up in any way there. So we'll talk about what that with respect to happens to mean once we get down here to example 2. But let's do very basically here in example 1. Example 1 says we have a function that is 3x squared plus sine x, and we want to find f double prime of pi halves. So that means we want the second derivative at pi halves. So the correct way to show somebody that you are doing this work is to write down your first derivative first. So derivative of 3x squared is 6x. The derivative of sine x is cosine x. And that's all we do. We then have space here to write f double prime, and that would be taking the derivative of each of those terms again. So now the derivative of 6x is 6, and the derivative of cosine x, remember, is minus or negative sine x, so it becomes a minus sign. So we first establish what the derivatives are, and then we use our notation to write f double prime of pi halves. Shows I'm about to plug that in. Right, and so if you needed to figure that out for a multiple choice test, sine of pi halves is 1, pretty sure. So 6 minus 1 gives us 5, okay? What we want to shy away from, I see students do this all the time, is that they write down, okay, maybe they put this problem down on their paper, copying the original, and then they just start taking the derivative with equal signs. So they say, that function equals its derivative, and then that equals 6 minus sine x. And they get to the same second derivative, but it's just notation is horrible. So please do not do it that way. Use your prime notations as we're going over today. Okay? Makes you look muy inteligente. Okay. Example 2 brings us a different notation. That Leibniz guy up here, right? So here we have a v function that is t to the 4th plus 6t minus 8. And this says to find dv dt at the value t equals 4. Okay, so in this notation, when we put a little number down there at the bottom, we are just talking about what number to plug in. So over here, it went in the parentheses for sign of pi halves, or when we plugged in pi halves. So we just use this evaluator bar, this is called. This guy right here is the evaluator bar, and we're going to do it still at t equals 4. So what we're saying here is to find the derivative of v with respect to x, right? If I use this phrasing, but these letters instead, right, in example 2. So all we're doing is we're saying dv dt equals, let's take the derivative, 4t cubed plus 6, okay? And I guess on this one, I didn't really say to find the second derivative. That's being super naughty. So I have a feeling that this, when I originally planned these notes, was supposed to say this. So let's just switch that up. And I'll probably switch it before I get to you, before the note sheet gets to you. But that means now that we're going to take the derivative again. So d squared v over dt squared is now 12t squared. And it's asking me to plug in 4. So my next move is to use that evaluator bar and put t equals 4 down here. And write 12 times 4 squared here. Oh my God, what is that? 12 times 16? I have no idea, you guys. How do you guys do math like this in your heads? I straight up do it like I'm 5 years old and put one on top of the other. But I think you guys were raised to be better mathers than I was when it comes to arithmetic. Oh, it's 192. Who knew? So that is our second derivative at t equals 4. All right. So we're going to take a little walk here and meet up with a good old friend. So it says calculus was originally called infinitesimal calculus because of how calculus breaks big concepts up into super tiny pieces in order to study how they change. A natural tie-in to the study of how things change is to look at our BFF physics. So we're going to go ahead and take a look at this graph. This graph is a distance graph, right? Also known, right? Sometimes refer to this as the position function or the position graph. It's measured in feet on the y-axis, time on the x-axis. And I want us to start thinking about slope at individual values, right, and what they mean. So let's think about the slope here at 0.5. That would be right here, right? And our slope at that point, if we steal it from this, larger segment, our slope is going to be 1 unit, right? So this means that this object or person walking or whatever it is traveling at 1 foot per second, right? And what I'm going to suggest here is that we would say, just common sense would say, like if it's just a person walking on flat ground or something like that, we might say the object is, moving to the right, in a positive direction from its point of reference. So sometimes we'll say that point of reference is the origin or whatever. So in this case, let's just think of it, as the origin. So how about the slope at 2? Changing colors here. So slope at 2, right, is this moment right here. The slope at that point, right, is 0. And what we would expect to see, right, is that this graph is not getting higher and higher. It's not gaining any position or gaining any distance, right? So in this particular moment, the object is standing still. Yay. So when we look at question C, and it says, what does the slope at t equals 6 tell us? Well, that's going to move us right here. And the slope at that point, if I kind of just count rise over run, right, is negative 2 feet per second. Okay. So the fact that this slope is negative, right, is telling us that this object is now moving back towards where it came from. Okay. So it's moving left from the point of reference, or backwards, if we think of it like moving forwards and backwards. Can't spell. Reference. Sound it out, kid. All right. So, we can obviously have negative slope, right? in a position graph. And that's what kind of brings us here to the next point, is that the fact that we can have positive or negative slopes tells us that velocity, right, which is the measure of how fast your distance changes, is a signed measure of change. So indeed, this tells us that velocity is the derivative of position. So this is notation that we have for these physics discussions, right, that we like to have in calculus class. So the first one, who knows why, but position in our class is typically denoted by S of t, and as we get into chapter 4, we'll eventually start talking about x of t and y of t, but for now, we're just going to use position S. If you go down farther, right, that's a distance measurement. It's a one-dimensional thing. If we take the derivative of S, we get velocity, right, which we can either call S prime or V of t. These two things are interchangeable with one another. You can use one or the other to talk about them. And of course, that is a measure of how fast you are moving. So our units for that is usually, feet per second, miles per hour, whatever the case is that we're measuring. And then lastly, down at the biggie bottom, if we take the second derivative, right, welcome to our use of higher order derivatives. The second derivative of position is the same as the first derivative of velocity, and that, of course, is acceleration. These three functions are all interchangeable with each other. Again, they all mean the exact same thing. And that this is, of course, a measure of how fast your velocity is changing. So distance per time, or I don't know, how do you think of it? Distance per time, or distance per time squared. So we always write meters per second squared when we talk about scientific measures of acceleration, feet per second squared when we talk about things in terms of feet, etc., etc. So we're going to have to be able to work with these functions in calculus as well as physics. And that's good for those of you that are enrolled in both classes. You'll be able to see the parallels. So example 3 is a nice, simple example. It says time is measured in seconds. An object's distance or position, right, is S of t equal to negative 16t squared plus 6t plus 48 in feet. Find the velocity and the acceleration of the object at t equals 3. Use proper notation and give units of measure. So I am supposed to find the velocity, right, and the acceleration. So I want to make sure that I'm paying attention to both directions here. Okay, and then I'll do my work accordingly. So what I'm going to write down first to find velocity is S prime of t, which is velocity, and I'm going to take the derivative of the function given, negative 32t plus 6. And I'm supposed to figure out that velocity at t equals 3. So I'm going to go ahead and show, working to the side here, v of 3 equals negative 32 times 3 plus 6, which I think is negative 90 feet per second, because it does ask us to include units of measure. Okay, this is my math right there, negative 96 plus 6. Looking good. All right, now I'm going to go ahead and take the derivative of that. So S double prime of t is V prime of t is A of t. You don't always have to write all three of these out, but it just helps us to process, where these values are coming from. So now the derivative of the green function is negative 32. There's no longer a variable there of t because it got wiped out in this differentiation process. So that means that my acceleration at 3 is negative 32. And then as far as units are concerned, that is feet per second squared. Okay. Just making sure, it's really just working on the notation and understanding velocity is your first derivative and acceleration is your second derivative. The last thing that we bring about when we talk about velocity, acceleration, those motion tie-ins is the calculation of average velocity, right? Because remember how we were talking about instantaneous rates of change and average rates of change before. Well, when we talk about velocity, we want to be able to calculate your average velocity over a given interval of time, A to B. So you can think of that as change in position over change in time, or, using that position function S, we're actually going to plug in, right, to get these two values. It's basically the slope, right, of this function at its endpoints, 0 and 5. in this case. So given position here, what I like to do is I just like to make up a simple little table. So at times 0, right? 0 cubed minus 0 squared is 0. Very nice. And then 5 cubed minus 5 squared. Man, these numbers today. What is this? 125 minus 25 is 100, I think. So we're now going to just find the slope between those 2 points, right? So 100 minus 0 for my numerator over 5 minus 0 for my denominator gives me 100 divided by 5. And my average velocity for this one would turn out to be 20 feet per second, miles per hour, whatever units they would give you. Okay, so that would be distance per time since it is a velocity.